Welcome to today's SCA webinar with Dr. Beryl Dinderuk of University of Houston and Dr. Seville Vescu of University of Texas on geothermal systems. Before we start today's webinar, I would like to ask some polling questions of the audience. So I'm going to launch the first question. What's your primary discipline? We have a lot of petroleum engineers in the group. The answers are coming in now. Quite a few geoscientists as well. And a fairly significant group in the other camp. So that's interesting. And some facility engineers. Still getting answers as some of you are joining. We're asking, what's your primary discipline? Quite a few people logging in. We have still the petroleum engineers are in the lead, followed by geoscientists and other, and facility engineering is last. Okay, the majority of you have voted now, so I'm going to share those results for our first question. We have 48% petroleum engineers, 38% geoscience, 10% other, and 5% facility engineering. So now I'm going to ask the next polling question. How many years of full-time experience do you have in the upstream oil and gas industry? Looks like we have some in every category. So that's good. Quite a good distribution in this group of experience levels. Answers are still coming in. It looks like the majority are in the 11 to 20 year experience level. Most of you have voted at this point, so I'll go ahead and close and share those responses. We have 35% in 11 to 20 years, and then a fairly even distribution among all the other experience levels. And then our last polling question is, how many years of experience do you have with geothermal projects? Answers are coming in. Quite a few of you have less than 1 year of experience. So we are here to learn. That's great. Okay, most of you have voted, and the clear majority, 88%, have less than 1 year experience. So thanks for sharing that information with us. So I will go ahead and introduce our speakers today. Before I introduce Dr. Dinderuk and Dr. Levesque, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature. We will cover the Q&A at the end of the presentation, and you will be anonymous. Today's talk is on geothermal systems, and Dr. Dinderuk has a long and illustrious career. I won't read all his accomplishments. Suffice it to say, he has been very active, a long career with Shell. Currently, he's a professor at University of Houston, and a number of accomplishments within SPE. And I think he's going to introduce himself as well, so we'll cover that in a minute. Dr. Levesque also has a very long engaging career. He's also served on a number of roles for SPE and worked for Baker Hughes and ExxonMobil before joining University of Texas at Austin. So we will get some more introductory comments from him as well. So our talk today is on geothermal energy, and this references a class that Beryl and Sylvia teach together. It will be offered in the public format in Houston, in our Houston Training Center in March and in August. But of course, you can set this up to be brought in-house if you are interested in having a private class. We have various free webinars throughout the years. And so just to put on your calendar, starting in January, and then again in June, we have 2 talks from Dr. Rajan Chokshi. Why and how gas lift is different from Gulf of Mexico to Permian, and production data needs some TLC too. And we have a new live online format that we've been offering as a response to COVID. And so we have Dr. John Lee will be speaking in this format on production forecasting for low perm reservoirs in March, and PRMS and SEC reserves and resource regulations also in March. That's a half-day format. And then, of course, SCA's training courses can come to your location. So we look forward to your calls for arranging some in-house classes. And of course, in addition to training, we offer consulting services. We do staffing, direct hire services, projects, and studies. So look to us for all your needs in those areas. So I'm going to give the presentation rights first to Sylvia. And
all right. So where do I get? I am the presenter now.
Yeah.
All right. So let me share my screen. All right.
So we're still seeing the polling answers.
Can you see my screen? No.
Okay. I think I've closed all the polls.
Right. All right. And here is my screen.
Now we see it. Very good. Thank you.
All right. So hello, everyone. I hope you can hear me well. It's a pleasure to be here. It's the first Geothermal Systems class that we are going to talk publicly about. And this is based on material that both Professor Dindoruk and myself are teaching at our universities. And so we will start. We have about 40-45 minutes, and then please go ahead with questions, and we'll try to answer them in the end. The outline of our talk today is, first of all, I'm sure all of you heard a lot about geothermal recently, and so we are going to address what is geothermal energy and why we are talking about geothermal now. Then we are going to talk a little bit about the GeoD project, and you are going to hear about it very briefly. And then we are going to jump into geothermal applications, geothermal opportunities for oil and gas. And I'm glad actually we did the poll in the beginning, because as you see, there are a lot of people from the oil and gas industry that are talking about geothermal as an extension of their skills, an application of their skills. And then we are going to narrow down for the rest of the presentation on 2 different applications that are relevant for, just giving you a little bit of context about where geothermal can fit in the entire energy transition narrative. And so one of those is using CO2 and supercritical CO2 for power generation. And another one is using direct air capture and geothermal together. And we'll end up with a summary of our talk. Susan was very kind to introduce ourselves, and so I put here a slide about myself with a little bit more details about my experience. So I come from the oil and gas, ExxonMobil, and most recently as the chief scientist for the pressure pumping product line of Baker Hughes. Long and very rich experience, technical experience in production engineering and well interventions and well simulation, production monitoring, literally, pretty much everything that we are doing in oil and gas. And so in the last, 3 years, I pivoted into sustainable production engineering, and that means hydrocarbons. It means carbon sequestration, but also it means geothermal. And so now I'm 100% into geothermal. I am a professor at the University of Texas at Austin, mostly in geothermal, and I'm a co-founder of Bedrock Energy, a geothermal heating and cooling system startup. I'm going to talk a little bit about it later. And with this, let me, I have the pleasure to introduce my colleague here, Professor Dindaruk. Susan, if you want to give presentation rights to be rolled. Thank you.
All right. Thank you, Silvio. Can everybody see my screen?
Not yet. Now we can.
Oh, okay. Okay. Thank you again. Pleasure to be here presenting with you, Silvio, and thank you for the kind invitation, Susan and SCA. Just a couple of liners over here, parallel to what Silvio talked about it. Born and raised in Turkey, actually, one of the geothermal hotspots, I guess, historically speaking. That's one of the earthquake zones as well. It comes in some places like a package. In fact, the map over here is intentionally drawn in a certain way. So Silvia and I, historically, we were not that far away from each other, although we didn't know each other. So I got my degree, BS, from Technical University of Istanbul, and in fact, the thesis was pressure transient analysis in geothermal systems. I did in a different style of degree over there with the BS with thesis. Then my other degree is a master's degree from University of Alabama. Is steam injection. It's again like related to heat flow in reservoirs. Then I switched gears in Stanford on the phase behavior side of it and how the transport happens in the reservoir, and you will be seeing some synergies between those topics, between these topics, as well as what Silvio is going to highlight as well. Then I worked on Amoco Corporation, which is taken over by BP actually later on, as everybody may know. I worked on reservoir simulation development projects. Falcon project was my last project over there, and it's now known as Nexus. It's another simulator in the industry today. Then I worked, my last industrial job was in Shell, and my last position was chief scientist of reservoir physics, and I had multiple roles over there. Right now, I'm a full-time faculty at University of Houston, and I focus on gas injection processes, CCUS, complex phase behavior, and of course, geothermal and heat flow, and flow in porous media in general is all part of it. Again, you will see some synergistic elements here. And for SP, similar to Silvio, I had many hats over here. Right now, I'm the editor-in-chief for all SP journals. So with that, I'm going to go into why geothermal. Why geothermal? So one of the first element over here, why geothermal? At least the motivation statement is that it's a renewable energy source because heat is continuously produced inside the earth. Geothermal is clean, always on. So that's one of the key points that you will see in the following slides over here. It has a small CO2 and surface footprint compared to other energy sources. So with the current initiatives, this becomes very, very important, especially net zero initiatives or reducing CO2 footprint. 99% of Earth is hotter than 1,000 degrees Celsius, and only 0.1% is colder than 100 degrees Celsius, actually. So geothermal for power generation, generally it's known as hydrothermal systems, the classical ones, and for direct heat applications, heating and cooling of buildings are mature and commercially available technologies. I mean, you can see many, many examples worldwide from low energy requirements to higher in certain places worldwide, including operation of turbines and energy generation. So why geothermal? Another thing over here, the pictogram here shows 4 elements over here to highlight why geothermal. Linear characteristics means over here is that, you know, we can multiply things. This is the total potential. This is a huge amount. And if we make 1% is a lot of energy, etc. That's the linear element of it once we access it. And we have the technologies to access a part of it right now. And also enabling technologies are getting cheaper as we speak. But again, going back to this pictogram over here or the sketch here, we have 4 elements: resiliency, grid reliability, low carbon intensity, low cost, and geographical independence. So if you were to draw a little circle or an ellipse in this case to show the spready over here, geothermal energy is located at the almost like middle of the upper part of that square over here. I mean, you can make it rectangle as well if you want, but what it means that it has the highlights over here is the resiliency, grid reliability, and low carbon intensity. But of course, there's a geographical dependence on it in terms of accessibility or cheaper to implement. But of course, it's not necessarily always low cost either. But it depends on how all these things are aligned. But one thing that I highlighted over here, which Silvio is going to dwell on it a little bit as well, is that the enabling technologies, the more we do it, they can also get cheaper. But the resiliency and grid reliability is going to be one of the key factors here. So it leads to the following over here slide. Capacity factor comparison. Capacity factor comparison for renewables, when we look at it, solar is 20%, wind is 45%, and geothermal is 90%. This clearly is leading in terms of capacity factor. So it's the percentage of time that a plant is generating electricity. So if you have very, very critical operations, that's going to be the key actually. So in terms of pricing things, if we look at worldwide, one of the premiums that we pay is the trust actually, how much we trust, or reliability actually. I mean, the trust itself is a chapter of its own actually. It's not only for geothermal, on many things that we do worldwide actually. So without getting into this thing, I mean, this is clearly highlights that factor here. So surface footprint is also very important actually. When we scale up things, when we go to larger scales, surface footprint is very important for many things. I mean, it can even be competing with agricultural products or cleanup or exit cost actually as well. So from that point of view, geothermal, compared to wind, photovoltaics, solar thermal, coal, it has this minimum surface footprint. And of course, this is more on the aerial side of it, as well as the footprint can also be seen in terms of what kind of peripheral harmful chemicals or other things comes out of it as well. In fact, if we include those kind of things, it could even be more important actually. For example, coal plant may have a 3,500 meter square level over here, almost like 7 times higher. But when you look at the pollutions, etc., other factors over here, it could even be more than that. So why geothermal now? So I'm gonna hand over this thing to Silvio, so he's gonna continue with this.
Okay, I'm going to change presentation rights, and I'd suggest you mute yourself, Burrell, to avoid any echoes.
I'll do that. Yes, thank you.
All right. So now I'm sharing my screen. Thank you, Birol. All right, so my screen, it's here. And let me go very quickly to, all right. So, does this look okay?
Yes.
All right. So why geothermal now? Of course, everybody knows that geothermal has been around for decades for, you know, power generation, for heating and cooling of buildings, and for other applications. The Romans, for instance, use it for, you know, 2,000 years ago and so on for different purposes, and the Greeks. But why geothermal now? So in the last decades, you know, there have been significant work for power generation, mostly done by the Department of Energy in the United States through national labs, trying to figure out how to maximize the amount of geothermal energy outside of, you know, the ring of fire resources. And so, for instance, we have this report since 2006 called The Future of Geothermal Energy. And then we have the GeoVision report since 2019. We have the flagship geothermal project under DOE called Utah Forge that is going now, and it's a great work done. But these are really just you know, small initiatives that have been left behind comparing to the other energy sources. So what happens is actually in the last, I would say 3-4 years, including myself, my story, my personal story, why actually I pivoted from oil and gas to geothermal is because of Jamie Beer. And so if you Google, for instance, she has a TED Talk. It's exactly on this topic, on how we can scale up geothermal energy in a meaningful way for the energy transition narrative by bringing the oil and gas industry and workforce into geothermal. And so Jamie was at the University of Texas before I joined here. So we still collaborated virtually at the time. And then at the beginning of this year, after more than a year of effort and more than 100 people have been involved in this, we came up with the Future of Geothermal in Texas, a grant through a report that is available online for free. And so please Google it and take a look. Both Dr. Dindoruk and I are lead authors on this. And so I may be biased, of course, but we believe it's a very important work in this discussion, and a lot of technical details about how Texas can become a geothermal producer. Oops. And then also because of Jamie, we can talk now about this GEOD project, which stands for Geothermal Energy from the Oil and Gas Demonstrated Engineering. So last year, Jamie approached me asking me how we can involve the Society of Petroleum Engineers. That is the largest professional society for oil and gas professionals. And so I presented this to the SP board when I was a technical director, and I got board approval for SP for the very first time to apply for a Department of Energy grant. And so together under Project Inner Space, for which Jamie is the executive director, with the Geothermal Rising, that is the society, the US Society for Geothermal Energy, and with the Society of Petroleum Engineers, we wrote a proposal, we applied for this grant, and we got approved for $165 million that is divided in 5 years, over 5 years. So in the first year, this consortium has to come up with a technology roadmap with all members that the Society of Petroleum Engineers and the Geothermal Rising have. And then for the next 4 years, we have to create different entities to apply for grants for developing those technologies. So the negotiations with the Department of Energy are still ongoing, and so I cannot talk too much about it, but stay tuned because hopefully in a month or so you will hear plenty of details about this project. So great initiatives, great momentum, and according to Jamie, this is going to be the geothermal decade. So now we have more time to talk a little bit about geothermal applications, and I'm sure you saw a lot of information like this. So long story short, after Birol talk about how our planet has plenty of thermal energy inside, many pictures like this can be found online. And so here is one on the left from the Australian Academy of Sciences. On the left, on the right is one from the US Department of Energy, the GeoVision report I mentioned earlier. And you can see here that depending on the type of the temperature, we can have plenty of applications for which we can use geothermal energy. Talking about the Department of Energy infographic on the right, on the left side, you see power generation using geothermal resources. And on the right side, you see a lot of other applications using direct heat. So that means instead of producing heat and then converting it to power, we just producing the heat, and then we use that heat directly for heating and cooling of buildings, for agriculture, for hydrogen production, for I mentioned earlier, for direct air capture and other applications like that. And so also from these infographics come from DOE. And so according to DOE, for global power generation, around 15,000 hydrothermal wells are in operation today, comparing with around 2 million active oil and gas wells, right? So the difference in scale is massive. And then for global district heating, the yearly market has increased from around 70 in 2000 to around 540 in 2022. And just to put this in perspective, then in green here, you see that DOE is predicting that using the current advancements from oil and gas for power generation using geothermal energy, we can provide by 2050 8.5% of the US generation with geothermal. And so that would stand for removing 6 million cars per year in terms of emissions reduction. And then on the right, for heating and cooling applications, the same DOE predicts that we can scale that up to more than 28 million residential installations, so for single family homes, and then to more than 17,500 installations, again by 2050, right? And this is equivalent of removing 20 million cars per year in terms of total emissions reduction, right? So just for you to understand the scale of the problem we are trying to solve, look again on how many hydrothermal wells we have currently, look how many district heating systems we have currently, and look actually where we need to be in 2050. From the report I mentioned about the geothermal future of geothermal in Texas, we polled 14 oil and gas companies in 2022. And so these are the answers. In terms of enhanced geothermal systems, pretty much all companies are interested. And so for closed loop systems, the same thing. For oil and gas well reuse, this was a little bit, divided. And so the reason for that is because oil and gas are designed especially for oil and gas production, right? So they are smaller wells that target especially hydrocarbon resources. And so in order to convert them, to retrofit them for geothermal resources requires some work that probably the oil and gas industry doesn't fully understand currently, and also doesn't understand fully the cost. And so for direct use applications, the same thing. Some of the companies don't understand exactly how to drill shallower wells for heating and cooling applications, how the business models look like, and things like that. But according to this survey that we did, you see that there is a clear, strong interest from the oil and gas industry into geothermal. Now, talking about geothermal systems, again, there are many, many flavors of these, and the discussions and the research, it's progressing really, really fast nowadays. So as you can see here, I have several pictures from my geothermal engineering class at UT. The first picture is from 2021, the first picture is from 2019, and the third picture is from 2020. If you ask me, all of them need to be updated based on what we learned in the last year. So none of this picture is actually complete anymore. But in order to give you an idea about what geothermal systems stand for, is truly about how deep we drill and how we are going to produce water or other fluids to bring the heat to the surface, and then how we are going to use that heat to at the surface for what kind of applications. And so for us, coming from oil and gas, coming from a subsurface engineering background, we can divide these geothermal systems in two main categories, right? So one category that is deep enough to produce so much heat to the surface that we can convert it to power, and then the other category is a little bit narrower, a little bit shallower, boreholes, wells, for which we produce still thermal energy to the surface, but then we can use that thermal energy, for direct heat applications without it converted to a different type of energy. And so if you just Google, you will see, and this is why I'm doing here this way, you will see that there is no standard terminology, taxonomy for geothermal systems. This is part of what the GeoD project, what SPEM Project Inner Space and Geothermal Rising are going to do next year. We need to come up as a community with a consistent taxonomy for geothermal systems. And so again, once you look at these pictures, you will see that there is no consistent way, to label, to classify all the geothermal systems. But again, to summarize them is just that how deep they go and what kind of, how much, what level of heat they are producing to use it for what kind of applications. Now, this is an infographic from DOE again, from 2021. And so I want to give you a different perspective of what we are going to talk here. If we want to drill deeper to convert, to have enough heat to convert it to power, in terms of energy quantity that we are bringing to the surface, if we drill to 200 degrees Celsius, and this is pretty much, about 55% of the surface of the US surface, right? It means actually drilling less than 10 kilometers deep vertically. We will require to produce 120 megawatts of electricity. This requires about 30 square kilometers of geothermal leases. We require drilling 18 injection wells and 24 production wells, right? So for those of you who are familiar with economics of drilling oil and gas wells, you can put a cost for this type of project. On the other hand, if we figure out how to drill deeper, and deeper means actually to 400 degrees Celsius, that means drilling to 20 kilometer vertically, and about 35% of the US surface. This shrinks actually to only 1 kilometer of geothermal leases and only 2 production wells and only 1 injection well, right? So again, try to figure out actually how to put a cost for the project on the left and the project on the right, and for you to understand the opportunity here to drill deeper for power generation. Now, for geothermal systems for direct heat applications, I'm sure you are familiar with this, but although we mostly talk about decarbonizing, transportation and mobility and different, agriculture and other systems, in terms of energy usage and carbon emissions, buildings are actually responsible, are the largest sector. So then it makes sense to decarbonize them using geothermal energy. And the technology is available today. We did this for decades, right? And I'm sure many of you heard about geothermal heat pumps or ground source heat pumps. And so here in the middle, there's a map of the geothermal, of the downhole temperature at different depths, very close to the surface, 20 feet in this particular situation, in which you see that pretty much anywhere in the United States, as a matter of fact, anywhere in the world, we have very, very close temperatures to whatever we need in buildings. And so it makes perfect sense for us to use that heat from underground to heat and cool buildings with clean energy. And with this, I'm going to pass it again to Birol.
Okay, I will pass the presentation rights, and Silvia, if you could please mute yourself.
Yes, I will.
Great.
Thank you very much, Silvio. Hopefully everybody can see my.
We see your slides.
All right, excellent. So this is a great segue to a couple of things that I want to talk about over here. One of them is CO2 for power over here. Sylvie already showed and highlighted a couple of things over here. One of them was how diverse or wide spectrum applications that we can find for geothermal, from local to regional. Other thing over here is that what are the guidelines or standards and taxonomy is actually. Those two key points are going to be probably a little more obvious by examples here as well. So when we look at geothermal applications over here, one of the technical challenges is how, when, and where to harness the energy. Of course, we want to do it fast, we want to do it economically. So accessible geothermal energy, the conventional one, at least the ones that we know historically, is hydrothermal systems that are basically in the outer crust. They tend to be in volcanically active areas, and they are dispersed in various places in the world, and they are US, Indonesia. Of course, there are certain regions within these larger countries like US, etc., and Philippines, Turkey. And one of the things that when we look at them as well is that these are the places that they are not major oil and gas producers, actually, excluding US over here. But of course, that's the size of it as well. In historical production of power at scale from only localized sweet spots. That's how we know them from the beginning. In fact, one of the oldest one over here is Larderello plant in Italy for more than 100 years in operation. But if you want to do more global beyond these sweet spots, so as to speak, or conventional systems, in other words, non-volcanic regions become also important, and it's also something that Sylvia highlighted over here. It requires drilling new wells or repurposing existing wells, and of course operating them at favorable conditions. Deep reservoirs, poor permeability is generally indicators for those as well. You may not have the water that natural occurring water in the system, in situ water that we can recycle and get the energy out. Economic technical challenges in heat recovery. Of course, this poor permeability is such problems, or no or limited water. So in those kind of cases, especially petrothermal or hot igneous containing significant heat type of situations, or deep dry rock or hot dry rock type of systems, power extraction becomes a different type of a problem because there's no in situ water, and of course in situ water has to be fed from somewhere, like in many of the hydrothermal systems. So in those kind of cases, we may have to use other fluids to extract the heat over here. So depending on the system, for example, if we use CO2 for heat extraction, the cycle that we name it normally is called organic Rankine cycle. Basically, in organic Rankine cycle, you can use higher molecular weight organic substances with lower boiling points, hopefully with the high heat capacity, so that you can, or latent heat, so that you can extract the heat at a lower temperature. So see, in many ways, CO2 is aligned with it, but of course, CO2 may not be the only one either, actually. So, if you look at fluid selection for heat extraction, can vary with the systems of interest. Long ago, for example, I worked on a system in one of the projects that I got involved back in grad school, was that we wanted to select what liquid metal to use for heat extraction from a reactor in a space probe. Totally different problem, but fundamentals are the same. So you need to select certain things aligned with the conditions of interest. And Sylvia already highlighted over here is that the conditions, depth, etc., can change quite a bit depending on the purpose. So also in terms of the scale of it, whether it's local or very localized, or a city block, or a neighborhood, when we look at it from this point of view, I look at the fact that nothing is too small. Everything adds up over here, actually, in terms of geothermal, because it can be widespread, wider than what we see today, and everything adds up for reducing CO2 also. We need to also look at from that point of view. I'm going to highlight another thing for CO2 in a bit as well. Let me just go through this one, the next slide over here. So limited pathways for flow, as highlighted in the previous slide. Poor permeability means that solution means generally is that it's something that we know already from unconventionals is that hydraulic fracturing or thermal chemical stimulation. Basically, you can expand your surface area in various ways. Insufficient heat carrying fluid, so it could be inject water and steam to get the heat that is needed, or inject other energy carrier fluid. So in this one, CO2 with a question mark. Of course, there are a number of publications, and we are part of it as well with Silvio through our collaboration, is that CO2 could be one of them. Of course, creating opportunity, coupling with CO2 sequestration, utilizing existing wells, future exit options for wells, and CO2 utilization, reducing the carbon footprint. But when we look at CO2 in a broader sense, the problem is even more interesting, which is a good connection to what the standards and taxonomy is. Like when we look at some of the hydrothermal systems, the in situ fluids or the brine or water that is contained in the reservoir can even contain natural CO2 and other gases. For example, I worked on a project on consultancy basis recently for a power generation company, is that they had CO2 in the water, and when they recycled the water, CO2 was out of it, and as a result, as they recycle water, the cold water is being reinjected, the reservoir was losing, or wells were losing their lifting characteristics. In other words, the system needed some boost in pressure in some way. Of course, adding CO2 is one of them. So another thing is that if you have gases in the system naturally or happening later on, how would you sample them? What is the steam water ratio, for example, if you are sampling? So these are, again, the question itself is also establishing the norms and standards for it as well, actually. So it's all related at the end of the day. So let me go to the next one over here. So one of the projects that we worked with Silvio, and is published as well, is that we looked at CO2 as a power fluid, and we looked at heat carrying characteristics in a well. So we basically programmed the entire thing ourselves. But of course, for this one, we needed CO2 properties in an explicit form so that we don't go tabulate these things or go and try to get it from various sources, etc. So we ended up characterizing the properties of CO2 for the entire domain of interest, very, very wide spectrum, actually. It's going from subcritical to supercritical. We were able to fit curves per, a family of curves, basically, per property. So you can take a look at this particular paper, for example, and you can program it to whatever the applications that you have. So we also deployed some of the things through our work here as well. And of course, the CO2, where it comes, etc., is also, or where it could come in a global scale or in a non-localized scale, is a good segue to the next topic here. And it will be, I'll give it back to you, Silvio, so that you can continue, actually. So all yours. Thank you.
All right. Thank you, Viral. Susan, if you, all right.
Yes.
That's great. And then let me share my screen. All right. So I have a little bit of problem. All right. That's it. All right. So now to continue Birol's drive into CO2, we can store it. We know how to sequestrate it, right? As subsurface engineers. Now let's talk about how we capture it. So one option would be direct air capture, which currently it's a tiny piece. As you can see here, the third bullet, we have only about 18 direct air capture plants operating worldwide, and they capture a tiny amount of CO2 from the atmosphere. And the reason for that is actually because CO2 is very diluted and it's very expensive actually to capture it, to separate it from thin air. And so one option would be to use geothermal energy, which can be, almost free, could be produced locally where the direct air capture plant is. And so we look at this in terms of problem definition. The International Energy Agency net zero emissions by 2050 scenarios, direct air capture technologies or plants are scaled up to capture almost 60 million tons of CO2 per year. by 2050, right? So it's a significant increase from where we are now. That's less than 7 years from now. So it's a significant drive towards direct air capture technologies, and so this is why geothermal can be an option. And so now with two of the students from the University of Texas, we look at how we can combine geothermal with direct air capture, and it's one particular type of direct air capture systems using solid sorbents that require temperatures only between 80 and 120 degrees Celsius. And so that goes towards, where geothermal energy can provide, with the current technologies, they can provide that level of heat. And so we did, actually, we have several papers involving the techno-economical analysis of direct air capture systems, solid sorbent using geothermal energy. And so we look at 4 locations. In one of the papers, we look at the Houston area. We look at the Los Angeles basin in California. We look at Alaska, Alaska's Cook Inlet, and gas fields from Netherlands. And so then in another paper, we have details about an open source code, techno-economical analysis, like this one you see here that we presented at the first SP Energy Transition Symposium that Birol and I have been co-organizing it. And so I'm happy to share more information if any of you can contact me, or you can just Google and find all this information by yourself. But literally now you can take this open source techno-economical analysis and you can just input your data for any field you want in the world, and you can see if geothermal would be an opportunity. Geothermal with direct air capture could be an opportunity for reducing the CO2 emissions for that field. And so I know we are running out of time. It's a lot of information here, and so the purpose of this webinar is really just to give you a flavor about what our class for our training course for CSA would be about. And so in summary, we talk about the GeoD project. I just wanted to give you a flavor about what it is, and so stay tuned because you are going to hear plenty of information coming up about it. This is the Geothermal Anywhere Decade, and so many opportunities for technology development and deployment for both power generation and direct heat applications are happening right now. It's a very, very dynamic landscape. A lot of people are jumping into geothermal and trying to help. It's a collaborative effort. I don't think only one person can solve everything, especially when we are under time crunch here to deliver something very fast at the scale needed. The lowest hanging fruit for decarbonization, I mentioned this, is can be achieved with geothermal heating and cooling systems that are available today, especially by retrofitting large commercial buildings. And this is what my startup is doing, Bedrock Energy. Now, what Birol and I touch on is that CO2 may be a good candidate as energy carrier for enhanced geothermal systems, leading to carbon mitigation and providing future options for wells. And so we can also talk about, as subsurface engineers, and scientists, we can also talk about how we can do CO2 sequestration and geothermal at the same time. And then in terms of carbon capturing, we propose a techno-economical analysis available for all, using solid sorbent direct air capture and geothermal systems. And with this, Susan, I think we are right on time. Birol and I will be more than happy to take questions.
Excellent. Thank you for the presentation. I'd like to remind our audience that you're muted, so you need to post your questions in the GoToWebinar question feature, and you will be anonymous. After today's webinar, you will receive a link to the recording of the webinar, an evaluation form, a link to SCA's website with more information about the training course Geothermal Energy, which is offered in the public format here in Houston on March 25th through 27th, and April 12th through 14th. So we're starting to get some questions. So the first question is, can you explain a little bit about slide 23 and 13? So if you go back to those two slides, please, and elaborate on slide 23 and 13.
All right, 13 and 23. Let me share my screen. And then share my screen.
Great. That's 14.
We don't have a slide 13.
Well, why don't you go on to 23 and we'll ask the writer which one he wanted.
Well, believe it or not, we don't have a slide 23 either.
Okay, well, let me go into the next question because we're continuing to get more questions here.
All right. I'll let my slides on the screen. So
okay, the next question is water treatment needed for the injection wells. Also, what other considerations do we need to account for?
Birol, you want to take that one, or should I start?
Yeah, you can go ahead, actually.
Yeah, so water treatment, it's a big topic. I'm sure, you know, coming from Baker Hughes, I spent a lot of time on produced water treatment. And so it's going to be a very hot topic in the future. For the legacy geothermal industries, they are already handled it from hydrothermal resources. Coming from oil and gas, actually, if we are going to do enhanced geothermal systems in Texas, for instance, then we have to talk about the same, you know, water treatment like we are doing for oil and gas, of course, with different chemistry, depending on the formation we are producing the heat from. And so this is a topic that I would like to see way more research than currently is done. And so again, stay tuned. If you have any ideas, by all means, I encourage you to contact Birol and me, and then get involved in SP, get involved in geothermal rising, get involved in GeoD any way you can.
Very good. The next question is this technology suitable for offshore?
Yes. So Birol, if you want to jump on it, you are more than welcome. Otherwise, I can take it.
I'll just highlight a little bit this thing, actually. You know, offshore, of course, it depends on how deep we go and what the losses, heat losses are within the system, especially from the subsea on, actually. And some of the offshore fields, the production, etc., is done through a network of pipelines. So, of course, there's a challenge. So whatever it is, if there's a long distance, then the power generation has to be on location. So that brings, in terms of repurposing, the space and weight requirements for platforms, etc. So it also depends on where it is. But at least I want that element of it, because I worked on just conventional oil production from offshore. They were always spaced and weight and the pipelines, etc. Plus the flow assurance, if you were to do it, even if it's a short distance. Of course, heat losses are going to be extra elements over here are the challenges. But I'll let Silvio to continue with the rest, actually, if anything to add.
Yeah, that's a great Birol. So I only add that in general, the way I look now at geothermal is power production or even direct heat applications. One advantage of geothermal would be to be deployed locally where it's needed. And so by doing that, actually, you reduce the, all the cost on the surface for building facilities, for building the power line and then the grid line, and so on and so forth, right? So ideally, because geothermal energy is everywhere in the world, we can build projects locally and use that energy locally.
Yeah, this is a great point, actually. It's got to be self-contained, maybe not huge amounts, but it will provide for local needs a reliable system, actually, to provide energy day, night, and in the middle of storms, even.
What is the energy density of geothermal wells, and how much energy can a typical geothermal well produce versus a typical oil well?
So there's not a simple answer for that, and so I alluded on this several times. It depends actually how deep you go, and then how you design your wells to bring that heat to the surface. It depends on how large your well is. It depends what flow rate you have, what kind of carrying fluid you have, right? So there are plenty of studies coming up with a lot of numbers depending on particular systems they are building. And so again, there is not a simple answer. There's not only one answer, and so we can talk at length about this if you want, but I encourage you actually just to look at what Forge is doing, Utah Forge, because they have plenty of studies, designing and studying the systems they are building in Utah.
Next question is, what is the time needed to explore and develop this kind of geothermal field as compared to oil and gas fields?
Yeah, so we haven't done. Birol, I'm sorry, if you want to jump into this, please go ahead.
Go ahead, actually. I mean, yeah.
So we didn't talk about this at all, but in terms of comparing oil and gas and geothermal, I think it's a completely different, it's going to be a completely different industry. It's going to be a completely different business model. And so the requirements are different, because here in Texas, for instance, when we did all this geothermal, future of geothermal in Texas report, and then this summer, the Texas legislature just passed, several bills for questions like who owns heat, right? So in oil and gas, we are used to have very well-defined resources, and we know very well our economics and everything, right? All the business models. For geothermal, it's not as clear if you are not in hydrothermal resources business. If you want to produce actually geothermal resources in Texas, literally, who owns heat? And how do you plan your economics for a geothermal project? And so we have to get together and come up with those standards, with those requirements, and with those, legal and economic, framework first. Thank
you. You mentioned there's no standard taxonomy for geothermal wells. How do you envision that playing out?
So we are working to we are going to work on that next year, and so we already have a draft, and we are inviting different experts to participate. Once we can talk more about the GeoD project, you will hear more about that.
What is the approximate cost of one of these deep geothermal wells to reach more than 20,000 kilometers, 400 degrees?
I wish I knew. So we are not there yet. First of all, we have to show that we know how to do that, and then we can talk about economics.
Tell us more about the GEOD grant. What will you be doing with that project?
I cannot talk too much because, again, the negotiations with the Department of Energy are ongoing, and so stay tuned. And so you'll hear more. If you are an SPE member or a Geothermal Rising member, you'll hear more next month.
And explain what solid sorbent means.
Right. So there are two main types of direct air capture systems that pass air through them and filter CO2 from air, separate the CO2 from air, right? The two main types are liquid solvent and another one is solid sorbent, which pretty much is a membrane that that has this coating on it, and so when the air passes through it, it separates the CO2 from the rest of the air, right? And it's a chemical reaction that happens between that solid sorbent, which is the coating on the membrane, and the CO2. And so that's what it's an energy intensive process. It happens, at that temperature between 80 and 120 degrees Celsius I mentioned earlier, and so you need to pass air through it. You need large propellers and a large volume of air to get a meaningful amount of CO2.
Thank you. Well, we've reached the top of the hour, so I want to thank everybody for participating in today's webinar. Later today, you'll receive a link to the recording of the webinar, an evaluation form, and a link to SCA's website with more information about the training course Geothermal Energy, which will be taught by Dr. Beryl Denderug, Dr. Sylvie Levesque. It's offered March 25 through 27 in SCA's Houston Training Center. Thanks very much. Goodbye.
Thank you, everybody.